you love looking at the night sky and find peace in it? Many of us are nyctophiles and just love spending hours looking at the beautiful twinkling stars. It makes us understand that we are just tiny specks of dust in this massive and interminable universe. But while sitting peacefully and watching those little twinkling objects, do you ever wonder how those stars were formed? How the whole night sky was formed? Just imagine that at some point in time in the past, there was nothingness, and then today we have trillions of stars in the universe. What is more interesting is that numerous new stars are still being formed while you watch this video. Excited to know the process? Well, I'm super excited to explain. So let us go. But before that, do not forget to like, share and subscribe to our channel in depth. Stars, as we see, are formed from dense interstellar particles, also known as dust clouds or molecular clouds. These interstellar spaces are composed of roughly 70% hydrogen biomass, while the rest is helium. These clouds of dust are called nebula, a bright ionized or neutral clouds of dust particles that are involved in stars formation. Hence, these places are also known as star nurseries. The best example of these nebulae is the Eagle Nebula that hosts the Pillar of Creation, one of the best photographs taken by the Hubble telescope. A typical spiral galaxy like the Milky Way contains star, stellar remnants, and a diffuse interstellar medium of gas and dust. Some part of this interstellar medium gets too dense to stay in a cloudy form, and the gravitation forces the particles to collapse under their own attraction, heating them to thousands of degrees of Celsius. This heated part is known as the protostar, where the term proto means primitive, and that is the part that will one day become the core of a young star. Gradually, more molecular cloud gets pulled towards the core, and the creation of star goes on. You might get shocked to know that a typical star formation takes roughly 50 million years to complete, much more than we humans can ever observe. However, quantum physics and modern computers have made it possible for astronomers to predict the complete process of star formation. Recently, 3D computer models of star formation have predicted that the spinning clouds of collapsing gas and dust may break up into 2 or 3 blobs, each creating a new protostar. Doesn't this ring a bell? Well, it does sound very similar to a unicellular division. For example, the mitotic division of amoeba, in which a single parent cell divides into 2 different blobs, also called as daughter cells. This step of star formation explains why the majority of the stars in the Milky Way are paired or in groups of multiple stars. There are hundreds and thousands of molecular dust clouds in the universe, but not all the clouds participate in stars formation. In any molecular dust cloud, the particles will remain in hydrostatic equilibrium, or in the original state, as long as the kinetic energy of the gas pressure is in balance with the potential energy of the internal gravitational force. In simpler words, the molecular cloud will remain static as long as the force exerted by the internal gas particles trying to move away from each other is equal to the gravitational force trying to pull them together. No star formation will start as long as this balance between the two forces continue. This balance may be broken by several galactic events such as a collision of 2 molecular clouds, shock from a nearby supernova explosion, or even intergalactic collision. Any of these events might send the molecular cloud into shock and initiate the gravitational collapse of them, starting the star formation. Moreover, these newly formed protostars might burst into a supernova and create a chain of further creation of the stars. The mass above which a cloud will undergo such collapse is called the Jeans mass. The Jeans mass depends on the temperature and density of the cloud and is typically thousands to tens of thousands of solar masses. Keep in mind that one solar mass is equal to the mass of our Sun. So for the process of star formation to start, mass of molecular cloud equal to tens of thousands of times of our Sun should collide. Hence, during cloud collapse, dozens to tens of thousands of stars form more or less simultaneously, which is observable in so-called embedded clusters. As the molecular cloud collapses, it breaks into smaller and smaller pieces in a hierarchical manner until the fragments reach stellar mass that does not have enough mass to form a protostar. The collapsing fragments start to grow denser, and as the process goes on, the core becomes opaque and does not let the radiation to pass on. This heats up the core to 100,000 Celsius. The cloud finally reaches hydrostatic equilibrium and now has enough density and temperature to slow down the gravitational collapse, becoming a complete protostar. Now, the molecular cloud is known as prostellar cloud. However, contraction of the protostar continues and the density as well as the temperature of the core keeps increasing until it is enough to initiate a deuterium fusion. Till now, a number of layers from the prostellar cloud have been added to the highly heated core, increasing the size. This phase continues till the surrounding gas and dust envelope is completely absorbed by the protostar. Now it is called a pre-main sequence star or a PMS star. Even after reaching the PMS stage, the energy source of the protostar is still the gravitational collapse, as hydrogen is not the only gas present in the core and the star is not yet stable. Gradually, the star will further contract till Hirschi limit is reached. This Hirschi limit works on the factor that a star with a certain mass will have a certain radius in a ratio that the inward gravitational forces are equal to the outward gaseous forces. When this limit is reached, the protostar reaches complete hydrostatic equilibrium and hydrogen diffuses into the core while other gases are completely moved out. This causes the surface to cool down and it starts using hydrogen energy. Now the star has become main sequence star and the formation stage has been completed. The best formation process is observed by stars with almost one solar mass. For larger stars, they have shorter formation periods and hence are not observed very well. The extramolecular cloud, if still left, may become planets or other heavenly bodies such as asteroids and form a solar system just like ours. In such solar systems, helium undergoes nuclear fusion to form heavy elements such as carbon, thereby creating a possibility of life as we know today. However, it is important to note that a star with a complete solar system is quite rare. Isn't it wonderful how something as big as a star is formed just from a cloud of gases? Observing the process of star formation helps us understand various aspects of the universe we are living in and tells us how even the most complex things are made up of simpler particles such as hydrogen and helium. So if the process is same for all the stars, then how could it be possible that out of the trillions of stars present in the universe, only our Sun got a livable planet? Seems intriguing, isn't it? Well, the astronomers already have found several Earth-like planets that they call them super Earths and might have possibility of life. But that is the topic for another day.